The general goal of these projects was to simulate and predict controls of semi-soft robotics. For the magnetic reconfigurable banding, this meant simulating and predicting control of an origami structured band using magnetic fields. This band would be embedded with magnetic particles, and in the presence of a magnetic field, would expand or contract as desired. In doing so, we would create a non-invasive method of constricting a given pathway in the body, such as an artery or intestine, for use in a multitude of medical applications. In order to optimally actuate this band, we had to create a model that could predict A, optimal orientations of magnets on an origami pattern, and B, optimal orientation of the applied magnetic field. The knowns M and B are varied in our calculation of work W, while variables L and N we can deduce from the origami pattern. First, magnetic field orientation B is fixed and magnet orientation M is varied. Then B is varied and M is fixed. The directions of M and B that produce the greatest amount of work are what we identify as the optimal magnet orientation and optimal magnetic field orientation, respectively. This model finds that optimal orientation is in fact identifiable, and that there is symmetry in the orientations. Figure 3 shows a 3x3 and 4x4 origami pattern with magnets on all faces, where the numbers indicate optimal magnet orientation of each panel in degrees from the x-axis. As you can see from the colors, many of these faces had matching optimal orientations in varying degrees of symmetry. In Figure 4, we see the magnetic field orientation was also identifiable. For a 3x3 sample pattern, it was found that changing the magnetic field direction 3 times over the course of folding produced the greatest amount of work. While this model provides us insight into orienting the magnets, further work is required on the subject of magnet placement and optimal configurations of the magnets on the band.